Okay, let's start. So stirring numbers of the first type. This is what you're learning today. Okay, so the question that we're interested in, distributing m distinct objects in n distinct boxes. So we want to distribute n distinct objects to n distinct boxes. We'll call this Tmn. This will be number of ways to distribute m distinct objects to n distinct boxes. Here's the catch, so that no box is left empty. Okay, so you need to distribute these into these with no boxes left empty. Stirring numbers of the first type will be this divided by n factorial, which will be naturally number of ways to distribute these into identical boxes. So when you have these are separate, but now boxes are identical. So no separation. So n identical boxes. This will, you can consider this grouping these so that you have exactly n groups. Remember that this is very separate, very similar to the question of actually distributing m things into n. So this is the number of ways to distribute m distinct objects to n identical boxes, so that each box has at least one element. So if I didn't have this condition, so that each box, can you do this? If I didn't have that condition, what will be the answer? If I had to distribute m objects into n boxes. So without this condition, it will be this cross and zero problem, right? So we'll be having m zeros, n minus 1 x's. So it will be m plus n minus 1, choose m. So the whole interest is with this condition. Because now you can't just say any distribution of zeros and x's is okay, because now we have a condition that each of these is actually has to be non-empty. Okay. So this new thing, which is almost like the permutation thing, m choose n or repeated permutation thing, turns out to be very different than all of these and has a very complicated formula. This will be the subject for this 1 hour. One easy observation is that if you distribute these m things into n distinct objects so that all of them is at least 1, you can see that as a two-step experiment where you do this as first step and then you number the boxes so that you get to this one. Uh-huh. Bu n-1'a da eşit. Because the number of crosses, right? These are the separators. Şu n-1, evet. But we have cross, how many separators you need? n-1 separators. M zeros.
But in the previous question it was n identical boxes, n different boxes and n identical objects distribution in this one, n distinct objects and n identical boxes.
I see, you're right. It's a different thing.
Actually, this time objects are boxes and boxes.
Okay, so let's be careful with this. So how can we analyze this question? So you want to...
Actually, you also need to include the permutations.
Okay, let's solve this one. Can we solve this one? These are numbered, these are numbered too. How many ways you can distribute this? Let's solve this one. So without this condition, let's solve this one. The answer is okay, let's think about it. I mean, each of them, you have n choices, right? So n choice, n choice, n choice. You will get n to the power n. This is that. Okay, let's go back to this one. So what's the answer for this one? Huh?
I think the answer was true.
That's what?
Previous answer was true.
Previous one was true. Why was the previous one? This one?
Because we have identical n-1 separators, and it doesn't matter. But the combinations in the boxes can be very different.
Yeah, when these are distinct, it's a little touchy. So if these were not distinct, okay, so this is the answer where these are distinct and these are. So this is without this condition. If the balls were identical, and the boxes are numbered, then the answer is m plus n minus 1, choose m. This is the case. Okay, so if the boxes are identical but these are still distinct, the box is identical, it only is one of the steps. So it should be n factorial, this thing divided by n factorial. So I think without this condition, you will be just getting this, all combinations divided by this. So that's what you get. I mean, not having numbers here and having numbers here, the only difference is n factorial.
This way, I mean, at this one object,
Yeah.
condition is remote.
Okay, so with the condition is also there's a similar relation. This is with the distinct boxes. So you're separating where they go in ordered way. Here you don't care. Because you don't care, this is actually mn divided by n factorial. Okay? So because of this stirring numbers, this is called the stirring numbers. Stirring number of the first type. There is also a second type stirring number, but we'll only care about the first type. This is the definition of stirring numbers first type. So this distribution problem, solution of this, or it is this distribution problem divided by n factorial.
But
That may not be an integer.
It is going to be integer. You'll see. Because all the distributions here will be multiples of permutations. Because we can permute your distribution, everything will be multiples of n factorial.
Actually, to me, there's nothing.
This one. Right. Okay, this one is the open question. So what's this one? So we want to find SMN, which is 1 over this. And we want to find formula for TMN. Okay? So how can we find the formula for TMN? This is the question. So let me write this in a different way. So this is we have m balls with numbers on it and n boxes with numbers on it, and we have a distribution problem. No boxes are left empty. Okay? So we want to solve this. We want to find a formula. This is how we do it. I mean, it's a little bit indirect way of calculating this, but we think is all possible ways of distribution of these with no condition is a big set. So this is no condition. No conditions. And we already calculated this. The number of these things, for each of these, you have n choices. So it's n to the power n. This is with no condition. But the thing is, we have condition, right? So no boxes should be left empty. But the conditions, we can actually think as this complement of bad cases. So what we want to count will be these complements of this. So TMN will be number of elements in the complement of bad cases. Now bad cases is a union. That's why we will be using inclusion-exclusion principle. Bad case is a union because the bad case means some boxes are left empty, right? So it's possible that you could have more than one box left empty. So they could have some intersections. So to make all the bad cases taken out, you define these sets. AI is the case where you do a distribution, but ith box is left empty. So this is the distributions where the ith box is left empty. So we can actually call everything, the whole thing is U, all distributions with no condition. So what we are trying to calculate is TMN. TMN is U minus union of these things. Okay, things in U, but not in the union. We have seen that when you have a separation like this is same as things in U minus things in the union. So there's no funny thing. This is just the difference of two sets. But what's funny is that unions is hard to calculate. This is where you need inclusion-exclusion principle. So we'll calculate TMN now using inclusion-exclusion principle. So what you get is TMN being this number of things in U minus the number of things in the union. It's going to be equal to number of things in U minus this plus minus plus and this. So it's just everything outside minus the ones inside plus the ones in the intersections minus the ones in the triples. So this is what we need to calculate. Okay. We already seen that number of elements in U, which is the universal set, which all the distributions, is n power m. Okay. This is n times n times n. This is the nature thing. But each of these we have to calculate now. Each of these we have to calculate. It turns out that the other ones are not very hard to calculate either. Okay? So, for example, what will be the number of elements in AI? AI is the distributions where you know the ith one is left empty and there's no other condition. So how many different ways you can distribute if you cannot use the ith box? Yeah, exactly. You can only use n minus 1 boxes, so you get this formula. How many different ways you can put things in if you cannot use ith and jth box? N minus 2. So this continues like this, which is a nice thing because now you know that intersections are always one less goes down. Which gives us a very nice formula for Tm. So Tmn is equal to n to the power m minus, each of these is n minus 1 to the m, but you see that the number doesn't change. It's always same on all of them, but you have n choose one of them, so you get this. Okay. On this row, each of them is n minus 2 to the m, but you have n choose 2 different terms there. So you will be getting n choose 2 terms. Each of them are n minus 2 to the power n. And it continues like this. So in the kth row, you get this. And choose k. This is the k intersections of AIs. So there are n, choose k of them. But this thing looks like n minus k to the m. And this is consistent because this is 1, this is minus 1. Okay? The last term is the n version of this. But then, actually, let me write the previous one. You get minus 1, n minus 1, n minus 1, 1m. And then last one is minus n, 0m. So the last term is 0 actually. So you finish with 1. The power goes down, you finish with 1. So if you write, for example, if you write 3, 3, 2, it's 2 to the 3 minus, so it 2 choose 1, 1 to the 3. This is what finishes. If you want to know 7, 3, 3 to the 7 minus 3 choose 1, 2 to the 7 plus 3 choose 2, 1 to the 7. So it has very complicated formula, as you see, but it is a very practical computation that you can always use now. This is it. Mm-hmm.
We found something for the stable number problem you asked, but we just included the last condition into the problem.
Mm-hmm.
We solved that way.
So stirring numbers will be this divided by 2 factorial or this divided by 3 factorial. Okay? So S32 will be 1 over 2 times this number. So this is 6. So it's 1 over 2 times 6, which is 3.
We have done this in a different way.
You know what?
In a different way. We
This-
put the one row in the n boxes first,
Uh-huh.
so that we guarantee that the no boxes will remain empty. By choosing n,
But that's only when you don't have numbers on them. When you have numbers on them, then it matters which number goes where.
since the identical boxes there are, if the first choice will not mean anything. So,
You're trying to solve this one.
yes,
Okay, so tell me.
after the first selection,
Uh-huh.
we just name the boxes.
Okay.
The remaining parts is just n exponential n minus n.
Without a condition, why you try to put one on each box
Not without condition. We
with the condition? With the condition, when these are numbered, I mean, it does matter who is with what. So if you first put 1 to each of them, the next ones will come, we'll make some of them like 3, 2, and it matters who is with who. So you get a different number.
calculate.
We could try one example. Let's look at, for example, this calculation, 3. Maybe it could be randomly through, but so you're trying to put 3 things, and you have 2 identical boxes. And each box will get 1. So you get 1, 2, 3, or 1, 3, 2, or 1, 2, 1, 2, 3, 1. These are all 3 cases. But if you say, let me choose 2 things to put on each of them, and then the last one will be put in 2 different ways.
One of the result will be repeated.
I mean, So who is going to go with, we can look at this 732. I mean, you cannot first do this and this because it's two steps, and which marks who is gone there first. So if you do this distribution process in two steps, what you're multiplying pairs, right? You're counting the pairs. So it will matter who went to the box first. So you'll be overcounting. There will be problems. But we have, I mean, it's not going to work because, say you put there's like 1,000 of them and there's 65 of them. You first choose 65 and put. And then the rest of them, when they come, it will see who were there first. But you don't want that. You don't want who were there first to be a part of your distribution. So for example, if you end up with this box having 30, who were chosen there first in the first distribution will be remembered. But you don't want to remember it. So you can't divide by 30 because you have different numbers on each box. Like, it will be mess. I mean, it's not going to count the stirring numbers. That's what I can say. Stirring numbers, I mean, it's mixed with many other counting problems we had. So you have to make sure that you see the point. But maybe this is a good discussion. The distribution in stirring numbers cannot be done in two steps. Because anytime you have a two-step, you are counting by multiplying this step and this step, you're counting pairs A, comma B. So you will remember this step first happened before this step. So it will be order choice. So if you are putting like 30 things here, who were there first in the first distribution will be remembered. And that's not a good thing. You don't want to remember who were there here first. We want just the distributions. Because of that, you can't do that way. Okay. Now, this is the formula that you will have to remember. And we will actually work on this formula to make it a little bit more familiar. And we want to develop things with it. Okay? So this is some form of combinatorics formula, right? Like we had M choose N combinatorics. So this is almost like that combinatorics formula. So when we had this N choose K, we use Pascal triangle. So this was a good way of remembering N choose K's. And the Pascal triangle worked by adding these numbers. So we actually had this formula. I might have written it different ways last time, but if you add the ith one with the I minus 1, you get the next row ith one. And this was the reason that you could use the Pascal triangle. Okay? So we will be looking at stirring numbers SMN. And we'll try to make sense of it. Okay? So let's put M here, N here. Let's calculate some of these numbers. So the question is, can you have a similar Pascal triangle relation with SMN? If we do, we don't have to each time calculate using this mass. Okay? So let's do some random calculations and try to see what you get using this formula. Okay, so let's start with S. 1, 1. So what's S11? 1 over 1 factorial T11. What is T11? 1. Because it's 1 to the 1 and you don't go anywhere. Okay, so 1, 2, 1. 1 over 1 factorial t2, 1. You can look at the formula. I mean, anytime you have 1, next time is 0. So it's always 1 to the 2. So it's 1, 2. You can see actually that as n m1, this is 1 factorial t m1, is always going to be 1 because this is number of ways to distribute n things into one box. And it's the only way to do it, put everything in that box. Okay? So these things are always 1. And it doesn't matter how you go down. It's a very nice thing. It's always 1. Nice thing is that the other one's also going to be like 2, 2, for example. How many ways you can put two things into two boxes? It's 2 to the 2 minus 2 choose 1, 1 to the 2. But this is equal to 1 over 2. 4 minus 2, 2, 2, 1. So you get 1 again. In a long way, but it still goes to 1. So S3, 3, for example, 1 over 3 factorial, 3 to the 3 minus 3 choose 1, 2 to the 3, plus 3 choose 2, 1 to the 3. You can calculate this. This is 27, 8, 3, 3, 24, 3, plus 3, 6, over 6, 1. So you get 1 again. This is one of the miracles of stirring numbers. You calculate such a complicated thing, you get 1 because you can only distribute 3 things in 3 boxes so that everything gets 1 only in one way. Basically, there is no other way. Okay? So because of that, these are all 1s. And the bigger ones are 0. So we get these numbers. It looks like a Pascal triangle almost. Like 1, 1, 1s, 1, 1, 1s. Now 3 choose 2 we did find as 3. So you can calculate a couple more to see if you are on the right track. 4, 2 is 1 over 2 factorial 3, 4, 2 is 1 over 2. Like this formula. 2 to the 4 is 16 minus 2. This is 7. So you get 7 different ways you can do this one. 1 over 3 factorial t, 4, 3. This is 1 over 6. 3 to the 4 minus 3 choose 1, 2 to the 4 plus 3 choose 2, 1 to the 4. 3 to the 4 is 27 times 3, 81. 81 times 3, 2, 2000. 3 to the 4. 200, 41. 2 to the 4, 43. 2 to the 4, 16 times 3, 48. So 195 plus 3, 198 divided by 6, 3. $33. It's a little big. Can this be 33? This is a little big, right? 243. It's 81 only, right? 81 plus 3 is 83. Minus 48. 50. 57. Yok. Yine yanlış. 4 dakika 16, 8, 48. 31, 33, 36. 36 divided by 6. 6. Right? So this is 6. Is that right? Okay, check the calculation. Okay, so the rest of the diagram goes like this. I can fill it in. So why those are the numbers? Anyone can see it. I can fill one more line if you want. So how did I get the next line? How did I get those numbers? It looks like Pascal. So some way you use these numbers to get this. So what could be the relation that could give you this number? It's not the sum of them. I did something a little bit more than just summing them up. What did I do?
It seems like for the second column, multiply by 2 and add 1.
Why 2? 2 has this number, right? If I did the same here, do I get the right numbers? So anytime you go down, you multiply with the number you see on the top. Okay, you multiply with this number, and then you, from this left-hand side, you just add it. So the claim is, this is the formula we claim, when you want to get Sm(n plus 1, oops, say Smn, I try to make this look like this, but I guess it's no hope. So I want to get like Sm plus 1 n, where n is this number, say this number. I get n times just one less than it. But from the other side, I don't multiply with anything. So this is your similar formula that you get for storing numbers. It turns out that, I mean, this is something that you can prove similar to this one, like using a combinatorial argument and so on. But this is true, and then because it's true, you have a Pascal triangle for these things. So it's almost like the kind of more advanced combinatorics. This is normal combinatorics that you probably know about, combinations and so on. This is a non-standard combinatorics. And it has many usages. Like many word problems, you have to solve only using Stirling numbers. If you write this S as a 1 over n factorial Tmn, 1 over n minus 1 factorial Tmn minus 1 plus 1 over n factorial times n as Tmn, you see a similar formula for T, that you get Tmn is equal to n times Tmn minus 1 plus n times Tmn. So you can see that this whole thing is n times the sum of these. And you can actually prove these formulas using a combinatorial argument for T. This one. Can you see why this is true in terms of distribution problem to boxes? This is the normal distribution. This is n times sum of some finite distributions. Any ideas how you can do this? Okay, this is a very simple idea. You choose one of the boxes. This can be done in n different ways. You choose one of the boxes. This is n different ways. Fix that box, and then look at the inside. The inside is number of ways. This has exactly one item or any items, like more than one item. I'm sorry, I forgot this n plus 1 here. You're right to get confused. So n plus 1 here. So we have n plus 1 items. Okay? So you choose this n different ways, and then you calculate the number of distributions in two different ways. You either have exactly one item, or you have strictly more than one item. With exactly one item, you take that one item out, and you cannot use this box anymore. So you have m things to distribute to n minus 1 places with exactly one. If you allow more than one item, then you assume that this is filled already, and then you look at the rest of them, but then the rest of them, you have exactly n different things you can go to, because you can go to that again. So this is the possible ways to go. Yeah, you can have combinatorics argument to prove this, and hence this one. Okay. Any questions? Any remarks? Okay, so see you Tuesday. We'll have a quiz to start with.